And we have already gone through the first few topics in the first set of lecture notes. And we have already covered the topic of the circular motion, as well as the energy of the systems and conservation of energy. So briefly summarize what we have seen. We have talked about the equation that governs the uniform circular motion. In the case of a uniform circular motion, we are talking about an object, a point object, if you like, moving in a circular orbit, and it is moving with constant speed. The speed is constant, but the velocity is changing continuously because the direction keeps changing. Magnitude of the velocity, however, is constant. So in this case, we could derive the acceleration of the particle because the velocity is changing, so there must be an acceleration. By deviation, we know that the acceleration points towards the center of the circular orbit. So that is the situation. The magnitude of this acceleration is equal to v squared over r. V is the magnitude of the velocity. R is the radius of the circular orbit. Of course, here you have a complete circular track, but even if you have part of the circular track, at the particular instance when the object performs the circular motion, it would have to receive a centripetal acceleration that is equal to v squared over r. And in order to have an acceleration according to Newton's second law, there must be a force, F equals to ma. So the centripetal force is the reason why the object can perform a circular motion. And the observation is when the object is making this circular motion, it has a centripetal acceleration. So there is a connection between the acceleration and the force. They are along the same direction, according to the Newton's second law. So if the centripetal force is present, it can perform a circular motion successfully. Otherwise, if, for example, the string is broken, there is no tension in the string, there would not be circular motion anymore. There would not be centripetal acceleration, and the object, according to Newton's first law, it would start to make a linear motion with constant velocity. That is what we learn in the Newton's laws of motion. So that is the idea of the circular motion. And of course, you could have a mixture of motions. Here, you have a circular motion in the horizontal direction, but the object is not moving up or down in the vertical direction. So circular motion is confined in the horizontal direction. So you could resolve the force components to figure out what are the forces that contribute to the circular motion and what are the forces that would be balanced in the vertical direction. We also talk about the car moving in a circular track. When the car is moving in the circular track, it has to make an acceleration that points to the direction of the center of the circular track. And this acceleration must be due to a force that points in the same direction. This force very likely is due to the frictional force between the tire and the road surface. And because the car is not sliding, it is not increasing or decreasing its radius of circular motion, therefore, it must be coming from the static frictional force because the car is not moving to increase or decrease its circular radius. Okay. So at here, we have also talked about the case of the vertical uniform circular motion. The acceleration is still pointing towards the center of the circular orbit, but where comes the force? In the case of this Ferris wheel, or in the case in general for vertical circular motion, it is a resultant force. The resultant force is due to weight as well as the reaction force in the case of a Ferris wheel. Or in the case of the object tied to a string, like in the case of the quiz question, it would be coming from the weight as well as the tension in the string. If the string has zero tension, then it would not be performing the vertical circular motion successfully. It would just drop and hit your head, basically. It must be performing circular motion only when there is a tension in the string. And that means you have to wheel your object in a high enough speed during the vertical circular motion. So we also talk about the energy of the systems. Some of the energies, mechanical energies in particular, you have learned it in the high school. For example, the kinetic energy or gravitational potential energy. We have just revealed the equations. But all this energy is related to the concept of work done. The idea of the work done is you have the force acting on an object. And if the force that acts on an object moves the object through a distance delta r, the energy associated with the process is equal to F dot delta r. Notice that F is a vector, delta r, which is the displacement vector, is also a vector. So this operation, which in the mathematics, it is called a dot product. The definition of the dot product for two vectors is this one. So you have the magnitude of the force times the magnitude of the displacement times cosine theta, where theta is the angle between the r vector and the f vector. So if you have the theta equals to 0, then the work done is positive. That means external force provides a positive energy, positive work done. This work done on the system would be given to the system, and the system gains energy. On the other hand, if theta is 90 degrees, then there is no work done. An example where you have F and delta R are perpendicular is just the circular motion. The centripetal force in the circular motion, is perpendicular to the displacement. It makes a circular orbit, and the force, which points towards the center, is perpendicular to the orbit. So they are perpendicular, so you do not expect work done in the case of circular motion. And because there is no work done to the circular motion, there is no gain in the kinetic energy of the particle. Think about it. In the circular motion, speed is constant. Velocity changes, but the speed is constant. So kinetic energy is constant in the circular motion. And there are actually situations where you have theta larger than 90 degrees and work done is negative. This would come a little bit later when we talk about the oscillation motion. And the case when you have a force that is varying and the performance work done can be considered by some of the classmates mentioned about the trapezoidal rule, but the general concept is you are adding up the area underneath the force versus displacement graph. every particular displacement through the journey would be associated with a certain force. And under the curve here, the shadowed one, the area is the work done over this particular distance delta x. So the general idea is you add up all these distances and you have the work done. Now, the displacement is along the delta x direction. So we are considering the force along the x. If you have the force along the y direction and associated with the displacement delta x, they are perpendicular. So there would be no work done. Of course, you would have work done if there is displacement along the y direction as well. But here, we are considering the component of the force. We are considering the component of the force parallel to the displacement. The component of the force perpendicular to the displacement contribute to zero work done. So that is an important issue. You only consider the component of the force parallel to the displacement. Or the other way around, you only consider the component of the displacement parallel to the force. Only that one is the useful work done. In the other direction, there would be zero work done. The work done is calculated as zero. So this would be the general idea of the work done. And of course, you have the kinetic energy as well as the potential energy. In particular, we have introduced the elastic potential energy. So that is coming from the elastic force due to the extension or contraction of a spring. And the spring force is proportional but opposite in direction to the displacement. Consequently, if you have an external applied force that extends or contracts the spring, the work done by this external force is equal to 1/2 kx squared. And notice that the x is the extension from the equilibrium position, extension from x equals to 0. So if you initially has already extended the spring, there would be already in some elastic potential energy stored in the system. And any further extension would lead to further storage of the energy. So you have to be careful in this situation. And the conservation of energy is just the consideration of the initial and final mechanical energies, at least for now, The initial energy plus the external work done minus the work done against friction would be equal to the total mechanical energy due to various components. And that is what we have seen in the last set of last topic. And we have briefly mentioned the case of the power. The power is the rate of change of the energy. So how quickly you input or take away the energy from the system, that is called the power. Similar to the case of the velocity or the acceleration, you have the instantaneous value, which has to be obtained, strictly speaking, by differentiation. Or you could have the average value, which is the total amount of the work done over a certain period of time. The unit of power is joule per second, or more specifically, it would be labeled as watt. So that is the unit of power. And because the energy or the work done is equal to force dot dr, and if you put it into the equation for instantaneous power, you will see that dr over dt is actually velocity. So the instantaneous power is equal to force dot velocity. this operation, once again, would be equivalent mathematically to F times V times cosine theta, where theta is the angle between velocity and the force. F and V, they are the magnitudes of the force and velocity respectively. So these are the topics covered in the units, I think 7 and 6 and 7. Now, we will move forward and start taking a look at another important concept in the linear mechanics, and that is the linear momentum. Once again, some of the concepts of the linear momentum you have already learned it in high school, so I could go through them very quickly. But I would try to do a quick revision because that is actually somehow a difficult concept for quite a bit of students. So the idea of linear momentum is just that it provides another tool for us to solve many linear mechanics problems. In the last few topics, we learned about Newton's laws. So we know that the motion of the object changes when there is an external force. So it will accelerate according to the external force. But in some situations, we may not have easy access to the force. For example, when you have an object that is moving from when you have an object that is attached to the spring, and when it moves over a frictional surfaces, then you have many different forces associated with it. So instead of just considering the force, another convenient way to consider the problem is to think of the energy. You have the mechanical energy, and also you have the work done against friction. So that is another possibility. But yet, there are situations in which even the energy change is not so obvious. For example, let us take a look in the case of a man holding an arrow, and he is trying to shoot the arrow. So what is the situation here? This man, when he shoots when he pulls the string on the bow, there would be some conversion of the energy. And when he released the bow would make some sound, of course. And when it shoots the arrow, there would be heating up in parts of the bow. So there would be conversion of energy, not simply mechanical energy, but maybe frictional force, maybe sound energy. In that situation, the energy calculation would be very difficult. Of course, we are not easy to have the access to the force because the force on the man as well as the arrow changes from time to time. So it is easy to say Newton's second law would apply. It must apply, but it is just difficult to calculate. So we need another tool in order to solve this type of a problem. The tool that we use actually comes from the Newton's third law. The Newton's third law is considering what we call internal forces, action and reaction force. So when you have the two objects, they are in contact with one another, and when one object exerts a force to the second object, so force on particle 1 from particle 2 on 1 by 2, it would be equal in size but opposite in magnitude to the force on particle 2 by particle 1. So this is the idea of the Newton's third law, action and reaction pair. Now, according to the Newton's second law, where comes the force? Well, what is the effect of the force, I should say? What is the effect of the force, according to Newton's second law, it would lead to acceleration of the objects. So you could rewrite the Newton's third law with the help of Newton's second law, ma for each term, m1a1 plus m2a2, and that is equal to 0. Acceleration is actually the time derivative of the velocity. So you have this equation, and with some manipulation, we could achieve a result that the quantities of m times v, the sum of m times v for the whole system has to be a constant. And this is basically another conservation law. The first conservation law we learned is the conservation of energy. Energy is not generated or not destroyed, it is conserved. You just need to include enough of the system. And at here, we are writing all the terms in the vector format because we want to show you clearly that these are vector quantities, because velocity is a vector. Of course, if you are just calculating the magnitude, you do not need to write the vector. You do not need to write the arrow. But you have to be very careful that these are vectors. So this is a very concise form of writing. Later, you will see that momentum, linear momentum does not occur in only one dimension. It could occur in 2 dimensions or even 3 dimensions. In that situation, you need to resolve velocity components. You can neglect the arrow on the top, but you need to understand that why we are writing this is because we are having vectors. So you could resolve components and have 2 equations in that situation. So the idea is every object associated with its motion, there is a linear momentum. And the linear momentum is just the product of the mass, which is a scalar, and the velocity, which is a vector. So the linear momentum by itself is a vector that has the same direction as the velocity, and the magnitude is equal to m times v. And mass has a unit of kg, v has a unit of meter per second. So the unit of vector, unit of a linear momentum is kg ms minus 1. If there is no external force, key term, external force, or net force, I should say, net is the really key term. If there is no net force acting on the system, then the total linear momentum of the system remains constant. That is the teaching of the conservation of linear momentum. And if we are really conscious about the Newton's second law, we will see that in the Newton's second law, F net is equal to ma, and it is equal to m times dv over dt. Mass here is generally a constant, so we could actually put it into the derivative. So when you combine m and v, it becomes the linear momentum. So the Newton's second law, in a more general term, it is actually the rate of change of linear momentum. You will see that it is not ma, but it is the rate of change of linear momentum. Now, this one actually has implication. Objects may be not changing the acceleration, but it may be changing the mass. When the mass changes, actually, the momentum would change. For example, you have a rocket, and the rocket carries some fuel. When the rocket is launching, it would be losing the fuel, so it would be losing the mass. In that case, even if the object has a constant acceleration, there would be a change of the mass. So there would be a change of a linear momentum. So the situation can occur. So that is something that we are trying to generalize the situation in general. But in here, we would be more focused, at least in this level, we will be more focused on the case where the mass is kept constant. So F equals to ma, or whether it's equal to the rate of change of linear momentum, makes little difference. So at here, we just take a look at a quick example. You have this man standing on a frictionless ice surface, so no external force. There is only internal force. And he is trying to fire an arrow at 50 meters per second. Initially, of course, the man and the arrow, they are both at rest. They are both at rest. And so we could apply the conservation of linear momentum. Initially at rest, so 0 linear momentum. Finally, it will be m1 v1 plus m2 v2. The arrow shoots to the front, from the left to the right at 50 meters per second. So we could rewrite the equation. V2 is 50 meters per second pointing in the I direction. Well, here it is a kind of a complicating the matter. We are considering only the motion in the x axis. So it has all the I vector here. So the I vector corresponds to the direction. So 50I means it is moving in the x-axis, in the positive x-axis, by 50 meters per second. And you could calculate what is the velocity v1. That is the velocity of the man after firing. So it is minus 0.42, meaning that he is moving backward. So just like you have a gun, then you shoot the gun, there would be a force that pulls you to the back when the bullet goes to the front. So that is some force hitting you back. Now, as we will see, according to the Newton's second law, the force is actually equals to the rate of change of linear momentum. So this rate of change of linear momentum, of course, you could write it in the you could rewrite it in the form of the average rate. So you could, instead of writing it as a differentiation, in a more easy to understand format, it could be equal to delta. I cannot write delta, I'm sorry. Well, maybe I could. Just you have to bear with it. It could be equal to delta P over delta T. Of course, I would notice here that this is a vector. When you write the questions, I mentioned it the last time, when you write the questions, as long as you recognize the direction, you do not need to write down the arrow. But you have to know that it is actually a vector quantity. So if your answers clearly notice that it is a vector quantity, either by considering the components or by writing down the term as a vector, it is okay. Well, for me, as long as you can get the right answer with the right concept, that is fine. The missing the arrow or not is not an important issue, because in many of the cases, it will be understandable whether it is a vector or not. But if your calculation misses the vector and you are clearly showing that you are just operating like a scalar, then it is a wrong answer. Okay. So it is okay to omit the vector. And the important thing is you know it is. Here, the force is equal to dp over dt. And it is also written in the average term, delta p over delta t. So we could rearrange the equation by writing delta p equals to the f times delta t. This is the idea of impulse. Impulse is a measurement of the change of linear momentum. Impulse is equal to the change of the linear momentum. And that is equal to the force times delta t. Now, what does that mean? When you have a change of momentum, there is something which is fixed. If you have a mass that is constant, if you have a mass of the object being constant, that means the velocity change is constant. For example, you have a car. You have a car at here. Sorry, I'm not wiping it out for the time being because I still need it. You have a car at here, initially moving at 15 meters per second. And then it hits on the wall and comes to rest. So initial momentum is the mass of the car times the 15 meters per second. Final momentum, mass of the car times 0. There is a change of the linear momentum. Nothing, however, is set on how the change comes. It could be the car hitting on a wall. So it takes 0.001 second for the car to stop. So for the same impulse, it could be a very large force happening over a short time. On the other hand, it could be the car hitting on a sponge, hitting on a very soft surface. So in that case, it would be maybe 10 seconds for the car to come to a stop. And the force would be much smaller. Of course, in general, you do not have a constant force acting on the car to change its velocity. It would be more likely the situation in this page. Initially, there is no force, and then the force increases gradually until it comes to a maximum, and then it drops again. So the contact time, total contact time, is Tf minus Ti, shown in this slide. The force keeps changing. However, we could always represent this situation, which is complicated, by an average force. So we assume the force acting on the, we could assume the force acting on the object being a constant. And so over the time delta t, the force acting on the object is a constant. And the total impulse brought about by this average force would be equal to the impulse brought about by this varying force. So the shaded area of the two would be the same. Now, important issue once again is delta t. If you have a very short time, no matter what is the shape, the average force must be large because the base is small, so the height of this rectangle must be large. So in order to bring about the change, you may need a very large force if you let the change occurs in a very short time. On the other hand, you allow the change to take place in a long time, then the force would be much smaller for the same momentum change or for the same impulse. So this is the idea. The impulse is just the change of the linear momentum. The impulse is a change of the linear momentum. How it occurs depends on the time. If the time is short, then the force will be large. Consider here the car smashing on the wall. If the car smashed on the wall in a very short time, then the force on the car would be very large. It would crash the car very hard. There would be action and reaction force. If somebody unfortunately is in the car, then the force acting on the man would be large. It would be likely the man to be severely injured. On the other hand, if the time is long, for example, you have a car that changed the shape a lot during the collision, then the time for the change would be long. The force would be small. So if you see a car hitting on the wall and you see the car changes the shape completely, what we call a total loss, then you would think that it is bad. No, it is actually very good because you protect the person in the car. On the other hand, if the car retains the shape, that means the change takes place in a very short time. And there is a very likely chance the person in the car to be severely injured, unless you have some other protections, like the airbag, like the seat belt in the car. So yeah, some student mentioned about Bruce Lee Kung Fu. Yes, if Bruce Lee gives you a punch, it usually is a very short time. So the force would be very large. So that is the idea. Now, let us take a look at the consequence of the change of a linear momentum, or the consequence of the velocity changes due to colliding objects. And this is the topic that would be very important in the linear momentum, and that is the collision of the objects. If you have a collision of the objects, typically we are considering a very large force associated with the collision. Just like when you have the two cars or two plugs hitting on one another, the force between them would be very large. There may be frictional force with the ground, there may be other forces associated with the motion, but because of the very strong internal force, we could neglect all the other forces. The interaction force are assumed to be much greater than any other external force. So we could assume no external force. And we could apply the conservation of linear momentum straight away. That is the idea. And we have two important types of collision events. The collisions could be elastic, or it could be inelastic. Well, the contact is not really necessary, because as long as the force is present, then that is an internal force. For example, you have two charged particles. Never assume that the two charged particles could be in contact with one another. According to the Coulomb's law, well, I just typed the word here. You could check it up. What is the Coulomb's law? According to the Coulomb's law, the force is inversely proportional to R squared. So if the objects are in contact with one another, the force would be huge. It would never be possible for the two objects to come in contact with one another. But yet, the force is always present between the objects. So the collision in that situation still occurs, and it does not require any contact. Of course, in many situations, say the collision of the plugs, the contact is still present. So there are two important types of a collision. One is the elastic, and one is the inelastic. Elastic collision is actually exceptional. it is not present very often. Only when you have microscopic level collision, for example, collision of the gas molecules, where there is little deformation of the gas molecules, then you will have an elastic collision. Or if you have a spring that is involved in a collision, then you could store the energy in the elastic spring, and that would be an elastic collision. Most of the time, it would be inelastic collision. In the case of an inelastic collision, kinetic energy is not conserved because some energy is lost somewhere. We do not even know exactly how much is lost. However, linear momentum is still conserved. So that is a very important concept. It is the linear momentum that is always conserved in both situations, but only in elastic collision, the kinetic energy is also conserved. So at here, we would look at the equations like the perfectly inelastic collision, which is actually simpler because you could only write down one equation. Initial momentum is equal to the final momentum, and that is written as m1 v1 plus m2 v2. Once again, if you recognize the velocities vectors, you could omit the arrows. But here you have only the motion in the linear direction in one dimension, so it is okay. So the final velocity is written in this way. For the case of the elastic collision, it is more complicated. I will not go into the details, but the general concept is you have two equations. The first one is the conservation of linear momentum. Second one, conservation of kinetic energies. From the conservation of kinetic energies, we could rewrite the terms. So here is just mathematics. By reshuffling the terms, we could derive an equation that is quite useful. And it connects the initial and the final velocities, apart from the linear momentum equation. So from that, we could derive the equations for final velocities for the two particles in terms of the initial velocities of the two particles. And we have some special cases at here for situations where the masses of the objects are equal, or if the mass of the objects are highly different. So these are the special situations. And once again, I'm not going into the details, but just try to take a look at some examples. Here, we have an object that is a block being hung by a string, and it is being hit by a bullet. Now, in order to solve this problem, we have to recognize what is the physical situation. Initially, the bullet is moving and the block is at rest, and it hits in, the bullet hits into the block. So we would anticipate the bullet would drill a hole, make some hitting to the block, energy lost. This situation cannot be easily calculated by conservation of energy, but we could use the conservation of linear momentum to find out the final velocities of the block plus the bullet, because the bullet is embedded into the block, so they move with the same velocity after the collision. After the collision, the bullet plus the block would be having excessive kinetic energy, so it would swing upward. This would bring about a change of the mechanical energy from kinetic energy into gravitational potential energy. So we separate the problem into two. First is the conservation of the linear momentum. Second, conservation of the mechanical energy. So we have to separate the two parts of the question in order to solve the whole problem. Never attempt to go from step one to the final step. They have to be done in stages. So the first stage, conservation of linear momentum. Second stage, conservation of mechanical energy. And then in the second problem, you have the two blocks coming towards one another, and the second block has a spring in front of it. So this would become an elastic collision. You could store the energy in form of the elastic potential energy of the spring, and later it could be released. So parameters are given to you. You are asked to find the velocity of the blocks after the collision. So the equations we could set up are, first one, conservation of linear momentum. Initial momentum, final momentum. The second equation comes from here, comes from the equation at here, this one, which is obtained actually based on the conservation of mechanical energy and the conservation of linear momentum. So we make use of this equation to assist our calculation. So remember this equation at here. I'm not saying you memorize it, but for the example that I'm talking about, this equation is the equation number 2 in the slide. So this equation number 2. Equation number 3 is just to multiply 2 by m1. Just multiply 2 by m1. So you will see the similarity between the number 2 and number 3. Difference is only the term m1. You multiply the whole equation by m1. Afterwards, you add equations 1 and 3 together, and then you could solve for v2f, final velocities of the particle number 2. So with that, you could solve for v2f, and of course, you would then solve for v1f from equation number 1. So that is the conservation of linear momentum, as well as the conservation of kinetic energy in case of an elastic collision. So in this way, we have to finish the lesson today. On Thursday's lesson, we would quickly summarize the first set of notes by going through the topic of center of mass. And we would work on 1 or 2 tutorial questions before we jump to the next set of lecture notes, which is concerned with the rotational motion, So rotation of rigid bodies around a fixed axis. Okay, so if any of you have questions, you are welcome to stay behind, and we will try to answer it to